In this video we are going to start matrices. Now, when we talk about matrices, a matrix is an array of numbers that is primarily used to either store values or to solve simultaneous equation. We are going to see how do we solve simultaneous equations later. Now I have written here three different matrices. So our matrix A, first of all let's talk about the size. Now size of an matrix is defined by saying its number of rows into number of columns, or it is said as number of rows by number of columns. We write it as, now in this case we have 2 rows and we have 4 columns. So we'll say size of matrix A will be 2 cross 4. This is not multiplication, this is just 2 cross 4. It says 2 number of rows and 4 number of columns, and we'll say it as 2 by 4. So A is a 2 by 4 matrix. And B, we can say that we have 3 rows and we have 2 columns. So the size becomes 3 by 2. And C is our 3 by 3 matrix. Now whenever we have a 3 by 3 matrix, or whenever we have same number of rows and same number of columns, we call it as a square matrix. So we can say we have a square matrix C of size 3. So we know that there are 3 rows and 3 columns. Other than that, if you see the matrix C, we have all the values as 0 except for the diagonal. So if we have all the values 0 except for the diagonal, it is also called as an diagonal matrix. If I had all values 0, all the values, if I had 0, then this becomes a 0 matrix. And if I had my diagonal values as 1 and all other values as 0, this will be called as identity matrix. So we have three kinds of matrix that we have seen. We have square matrix, we have diagonal matrix. Diagonal matrix is going to be a square matrix because, as you can see, in B part we will not have a perfect diagonal. This will not be called as diagonal. Here also we will not have a diagonal. This will also not be called as a diagonal. So diagonal matrix has to be a square matrix. An identity matrix should also be a square matrix. Now we'll talk about transpose of a matrix. Now if I say I have a matrix A, AT is said to be the transpose of a matrix, or we can also write it as A dash. These are the two ways we can represent a transpose of a matrix. Now transpose is nothing but if we change our columns with rows and rows with columns, then we get a transpose of a matrix. So here we had 2 by 4 matrix. Now if I make it into 4 by 2 matrix, then it becomes transpose. Now how do we make it? We say our first row becomes our first column. So we'll have 1, minus 1, 3 and 5. Then second row becomes our second column. So 3, 4, 6 and minus 4. So in this manner, this becomes transpose of our A. So if we make transpose of our B, so we'll say B transpose. Now here we had 3 by 2, so now it is going to be 2 by 3. So we'll have 2 rows and we'll have 3 columns. So our first row becomes our first column. So we'll have 1 and minus 3. We'll have 2 and 5. We'll have 0 and 9. And for our C, first I will take this 2, 3, 1 so that we can see the transpose. So we'll say C transpose will be equal to, now for a square matrix, transpose size will also be same. It will also be a square matrix with the same size. But our first row becomes our first column. So we'll have 2, 0, 0. Second row becomes our second column. So we come 0, 3 and 1. Sorry, 0, 3 and 0. And our third row becomes our third column. So 0, 0 and 1. Now as you can see, it is the same matrix. Our transpose is exactly same as our original matrix. So if a transpose is same as our original matrix, then it becomes a square matrix. It has to be a square matrix. Otherwise, you can see in any other cases, our matrix size is changed. In our A transpose, the size is 4 by 2. In our B transpose, our size is 2 by 3. And here we still have 3 by 3, and you can see the actual diagonal has not changed and all other values were actually zeros. So this becomes a diagonal matrix. So definitely, if this was not a diagonal matrix, if I had, let's say, 2 5 7, so I would have got here 2 5 7. Now definitely these two matrices are not exactly same. Their size are same, but the matrix is different. So not all square matrix will have their transpose equal to the original matrix, but if we had a diagonal matrix, then definitely the diagonal matrix transpose is going to be exactly same. So this is all about the transpose of a matrix. Now let's talk about addition or subtraction of a matrix. Now first of all, we can add or subtract a matrix only if the size is exactly same. If we had two matrices of two different sizes, we will not be able to add or subtract those matrices. So here we have taken our two square matrix of size 3. If we want to add, we'll also get another matrix of size 3, in which what we'll do is we'll add up our first elements, or you can say corresponding elements. So 2 plus 4 will get 6. Then we'll add up our second element, we'll have 7. We'll add up our third element, so we'll get 3, and so on. So we'll get minus 12, then minus 3, minus 5, 4, 7 and 3. So this becomes our A plus B matrix. Similarly, we'll subtract our corresponding values. So we'll have 2 minus 4, so minus 2, 4 minus 3, 1, 2 minus of minus 5, so 7. We'll have 4, we'll have 7, minus 7, 7 into 3, 7 minus 3, we'll have 4, minus 5 and then 3. So in this manner we can add or subtract two matrices of the same size. If the size is different, we will not be able to add or subtract. Then if we have a constant multiplied, so if I need to find, let's say, what is 2 times A, if I just have a constant multiplied, our matrix, each value will be multiplied by that particular constant. So we will have 2 into 2 4, then 2 into 4 8, then we'll have 10 minus 8, then 4 minus 12, 14, 2 and 6. So we have just multiplied our constant to each and every value. So these are the few arithmetics that we can do on a matrix. We can find the transpose, we can add matrices, we can subtract matrices, and we can basically multiply a constant to a matrix. Then we'll move on to a matrix multiplication. Now whenever we multiply two matrices, if I have one matrix A, B, C and D, I have another matrix E, F, G and H. If I am multiplying these two, what we do is we take our first row of our first matrix, multiply it with our first column of our second matrix. So row into column. So we'll say it will be A into E and then B into G, and we add up. That becomes our first element. Now you can see our first row and first column. This first row and our first column, the common part is our first element. So there we write our multiplication and addition, whatever you want to call it. Similarly, we'll do it with our first row and second column. So we'll have AF plus BH. That becomes our first row second element. So because the interaction, or you can say the common part of my first row and my second column was this particular my second element of our first row. And similarly the third one, we'll do the second row and our first column. So we'll have CE plus DG, and that becomes this. We'll have CF plus DH. So this is the matrix we are going to get. And so let's say this was our A and this was our B. So this becomes our A into B. Now what if we had B into A? So this was our A and this was our B. So B into A, we'll have E F G H multiplied with A B C D. So we'll take our first row from our first matrix, multiply it with first column of our second matrix. So we'll get AE plus, we'll have F into C, or I'll write as C into F, CF. Then first row, second column, so we'll have EB plus, I should write it as BE. BE plus DF, and then we'll have second row first column AG plus CH, and second row first column BG plus DH. Now if you compare these two, in our first one, first element was AE plus BG. Here we have AE plus CF. Now we actually did not have any such element AE plus CF. So this A into B and this was B into A. So our A into B is not necessarily equal to B into A. Rather, majority of the time our A into B will not be equal to B into A. So therefore, the order of multiplication of a matrix is really important. Our A into B may or may not be equal to B into A. And when we are multiplying our matrices, it is not necessarily that they should have exactly same order, but there is a catch. If I say that I have a matrix 2 1 3 that is of order 1 row and 3 columns, so this becomes 1 by 3 matrix. And let's say if I have a matrix 1 3 and minus 2, so you can see we have here 3 into 1. So our first matrix was of size 1 by 3 and the second is 3 by 1. Now I can actually multiply these two matrices. I will get first row into first column. So I will have 2 into 1 2 plus, we will have 1 into 3 3 plus or minus, because of minus 2 we will have 3 into minus 2, that is minus 6. Now other than that, I do not have a second column in the second matrix. I do not have the second row in my first matrix. So this is the only combination that we are going to get. So now this is a matrix of order 1 into 1. So our final value is going to be -1. So this becomes our multiplication of this matrix. So whenever we are multiplying matrix, our number of columns in our first matrix should be equal to the number of rows in our second matrix. That is very important. If that is not true, we will not be able to multiply our matrix. So number of columns in our first matrix should be equal to number of rows in our second matrix. The other values can be different, but these two has to be same. Let's talk about determinants of a matrix. Now determinants is a scalar quantity associated with a square matrix. So first of all, whenever we are trying to calculate a determinants, we need a square matrix. And we say if we have a square matrix, our determinant written as det of A, or it will be mod of A, or you can write it as delta. These are the three ways of writing a determinant, is going to be a scalar quantity of a square matrix. Now let's take a matrix A into consideration. We have 2, -6, 4 and 3. Now to find the determinant of a matrix, what we do is we multiply diagonals. So we'll say 2 into 3 and then 4 into -6, and we subtract these two values. So we'll have 2 into 3 minus, we'll have 4 into -6. So we get the 6, and this will be 24, and that becomes plus, so we'll have 30. So we'll be able to find determinant of a 2 by 2 matrix in this particular manner. Let's take another example B. If we have 3, 5, -2 and -7. Now see, we can only have determinant of a square matrix. So the determinant of B will be equal to, we'll say 3 into -7 first diagonal minus of -2 into 5. So this becomes -21, -10 plus 10. So we'll have -11. So as you can see, we will have a scalar value. There is no direction, there is no array. So there is only one single value. That becomes our determinant of that particular matrix. So this becomes 2 by 2. What happens if we have 3 by 3? So if I say I have a matrix A such that I have A, B, C, D, E, F, G, H, I. So I have a 3 by 3 matrix. Now in this, what we do is we take any row, or basically any row. We can take any column as well, but we find an associative matrix for it. So if I say I am taking my first row into consideration, out of which my first element is A. So its associative matrix is going to be this. So I remove the row as well as I remove the column associated with it. So the left matrix, or the whatever value is left, is going to be my associated matrix with that particular number or that particular value. So for this A, the associative matrix is going to be this small matrix. Similarly, if I take B, so my second element of my basically first row, I will remove the row and I will remove the column, and whatever is left, that is my associative matrix for B. That will be D, F, G, I. Then if I consider C, the associative matrix is going to be this D, E, G, H. So in this manner, we'll find our associative matrix. We can do it for any row or any column. And for one row and one column, what we do is we say our mod of A or the determinant will be, first of all, we'll say A into determinant of our associative matrix. So associative matrix for A was E, F, H, I. Then minus of B and then its associative matrix. So we'll have D, F, G and I. Then we'll have plus C and then associative matrix, determinant of that we'll have D, E, G and H. Then we can find determinant of each of this 2 by 2 matrix as we have studied it earlier. So we'll have A times, we'll have EI minus FH, then minus B times, we'll have DI minus GF, and then plus C times, we'll have DH minus EG. So this becomes our determinant of a 3 by 3 matrix. So it's very important that our second element of our row or our column, whichever you take, is going to be negative. So we'll have plus, minus, plus. If I had 4 values, 4 by 4, I will get an associative matrix of 3 by 3. Now we are not going into 4 by 4 because it becomes very long and we have only one way of solving. From 4 we'll convert it into 4 different 3 by 3 matrices, and then from 3 we'll have to convert it into 2 by 2, and it becomes very long. So it will never be asked to find determinant of a 4 by 4 matrix, but 3 by 3 is a fair game. So if I say I want to find determinant of A, where I am saying my A is 1 minus 1 2 3 0 minus 4 and 2 minus 3 and 1. So this becomes my A if I need to find mod of A. So mod of A is going to be, now you can take any row or any column. So let's take into consideration our first column. I showed here using our first row, I will take first column. So our first element of our first column is our 1. So we'll have 1 into our associative matrix. So our associative matrix of 1 will be, we hide our first row and our first column. So whatever 4 values are left, that becomes our associative matrix. So we'll have 4 minus 0 minus 4 minus 3 and 1. Then we'll have minus our second element, that is our 3. Then we hide up its row and its column. So we get minus 1, 2, minus 3 and 1. Then we'll have plus 2 and we hide up that row and that column. We'll get minus 1, minus 1, 2, minus 3 and 1. Then we'll use our cross multiplication. So we'll have 1 into 0 into 1, 0. So just write it as 1 into 0 minus of minus 12 or plus 12 actually. So minus 12. Then minus 3, we'll do the same. We'll have minus 1 into minus and minus plus 6. then we'll have plus 2 into minus 1 minus and minus of plus 6. I think I did a little bit of mistake when I took this is not the associative matrix. We will hide up our first column and third row, so we'll get minus 2 2 0 and minus 4 0 and minus 4. So here we'll get 4 minus 0, so we'll get minus 12. This becomes plus 5, so minus 15, and then plus 8. So our answer is minus 19. Now you can try this with any row and any column. If you do it correctly, you will always get minus 19. You should always get minus 19. So you can find determinants in this particular manner.